Oh, hello there. Hey guys, what's going on? Memes here. Yes, we're back. We're back. What are we talking about today? Well, for those of us that have been following the physics, especially within the realm of high energy physics, particle physics, if you would, apparently there's a new proton in town. Something you may occasionally hear the term. It's the GCC proton. What the heck is that? Well, let's not belittle the point. Let's share with the class and get to it. So, basically, long story short, what happened is scientists at CERN's LHCb experiment, basically B for beauty and everything, aka the bottom quark. Uh, Basically, they discovered a new proton where your normal proton, as we understand it, within the standard model, is made from two ups quarks and one down quark. This is the same thing, except our up quarks have been upgraded to the second generation of particles, aka the charm quarks, which are a lot more massive than our standard up quark friend, leading to a proton with a mass about 4 times the standard proton. Okay. And then it's got this normal down quark. Long story short is it does seem to be quite unstable. Imagine that. Imagine that. This thing where protons, as far as we know it, appear to be stable. Under some grand unified theories, they may decay after about 10 to the 35 years. Those are some of the estimates that I've heard. Again, take it with a grain of salt or a glow-on of salt, perhaps. Something like that, pun intended. But let's get into it. So you can easily find this stuff by simply just type, or at least on my internet, because apparently everyone else's internet is different. Type in proton, charm quark. And you'll all see all these things. LHCb collaboration one day ago. Scientific American one day ago. All right. Evidence. Oh, so there was evidence back in 2022. Very interesting. You get the charm quark over here. Okay. So let's go to our Scientific American article where we totally stole this image from. Okay. So as you can see here, a charmed new particle is discovered at world's largest atom smasher. Large Hadron Collider just produced a never before seen particle made of charm and down quarks. You can see this is an artist's rendition. What do we have here? We're putting like a sphere on it. Why? Because spherical cow. And then we're representing these as just more spheres and just random like linked glue-on interactions, whatever those may or may not be. But as you can see here, it's the constituent components appear to be 2 charm quarks and 1 down quark. Then we get the symbol over here that I remember from the Wolfram Physics Project. This over here is pronounced G. It is the 14th letter of the Greek alphabet plus, aka its meaning it has a positive charge, and then CC, basically highlighting it's made up of 2 charm quarks. I am making a very generalized assumption because that's basically what it is. It's another version of a proton, and it just happens to have 2 charm quarks. Okay. As we can see here, physicists just discovered a brand new particle that appears to be an exotic cousin to the protons and neutrons that make up atoms. Those mundane subatomic particles are made up of even smaller building blocks of matter called up and down quarks, which are the lightest kinds of quarks. But quarks come in heavier flavors as well, including charm, strange, bottom, and top. The most massive fundamental particle. So long story short, what is it? Like an up and down quarks are like a couple of mega electron volts. Okay. When you go to the far end, the top quark, it appears to be 173-ish giga electron volts. For those of us not up on prefixes, mega means millions. Okay. Within particle physics, very often you'll hear the term electron volt. Why? We can use it for essentially anything. We measure its length, electron volts. We measure its mass, electron. What is it? It's a unit of energy. It's what is electron volt is the amount of energy used to accelerate like one electron or something. A very small amount of energy. But we use it to help quantify what is going on. So basically, you up and down a couple of mega or millions of electron volts. At the far end, the extra beefy top quark, yeah, it's like 173 billion times, aka it's got the mass of about 173, 175 protons there. That's freaking crazy. That's not what we're talking about. We're talking about the charms, which are upgrades. So let's go to our friend Wolfram Alpha, charm, quark. Let's look at the stuff that's going on here. Okay. Well, as we can see, this is very interesting because the mass of the charm quark by itself is more than the mass of a standard proton. About 1.3 masses there. Oh, that's kind of weird. So let's do this. Do the charm quark mass. And then we'll multiply it by 2. 2 charm quark mass. Okay, it gives us this. Now I'll add in 1 down quark. 1 down quark. Okay, so it's basically a little over 2.5 times the mass of a normal proton. Actually, hold on. Let's just take this. Let's see what it comes out to be, because there's going to be binding energy as well. So divide by proton mass. All right, 2.723. So that means there's still like a whole bunch more binding energy, because they're saying that it's about 4 times the mass. So that's close to 3. So we got another proton of binding energy for that. So we got that. So how about this? Plus x kg equals proton mass. Oh, no, equals 4 proton masses. That's where we go. All right. So that would mean that this particle would weigh kilograms divided by proton mass. Okay, so it's going to be about 1.5 times proton. Okay, 1.2 times the proton. I'm just literally, if they say it's 4 times the mass of a proton, we're just setting it equal to 4 times the proton's mass. So the binding energy, if we got 2 charm quarks, it's got about 2.5 giga-electron volts of mass energy. And then we add in the down quark there. Okay. So that means the total binding energy that's required is more than the total mass of the proton itself, or at least with up quark constituents. It's kind of rad. It's kind of rad. Well, there's more massive things. It's going to use more energy and stuff like that. And all right. Very cool. Very cool. All right. Let's go back. So let us continue with the Scientific American article. And again, the links to all this stuff is in doobly-doo below. All right. Where are we? Let's see. All right. A new particle discovered in the world's largest hadron special, the Large Hadron Collider, aka the LHC, in Geneva, Switzerland, consists of 2 charm quarks and a down quark. Like protons and neutrons, its total of 3 quarks classifies it in particle physics as a baryon, which is a type of hadron, or a particle made of quarks. The discovery brings the current tally of known hadrons discovered by the LHC experiments to 80. Okay, all right, hey, man. We're discovering some new things. Now, again, we have models that these seem to be a thing, so we kind of thought that they should be possible, but just because you think it's possible doesn't necessarily mean it's possible. If you have the possibility to actually make something and actually detect it, and again, what is a detection? What is a measurement? Our detector goes click. Okay. Whatever that click may be, whatever that magnitude may be, whatever the frequency of the clicks might be, our detector detects something. To the best of our ability and our scientific process of isolating the infinite number of potential variables that could go wrong. Not an easy thing. All right, let me hold on. Let me undo this. Just a second. We'll get to what Anton's found. Oh, a gigamazer! Wow, I'm gonna have to look at that next. Like I like giga because that's actually we're just talking about that. We're talking about mega, millions, giga, billions, and then tera is trillions. All right. Oh, and Pipe is actually streaming. Okay, it's we've got the rollover that will roll over to Pipe stuff. All right. Let me just make sure that. Okay. All right. Every once in a while, you just gotta check to make sure it's actually working with all the stuff and things. All right. So let's go back over here. Back to a window. We don't need a pry over there. And boom, back to Scientific American. All right. All these advertisements. All right. All right. The new particle, which physicists are calling a doubly charmed baryon. Sounds like a charming thing to do, hence the pun in the title. All right. Essentially, it replaces the two quarks and a proton with charm quarks, giving it about 4 times the mass of the more common and stable proton. The LHC accelerates protons to more than 99% the speed of light and slams them together. That's obviously how God intended it to be. The protons are destroyed, and the energy of the crash gives rise to new particles in their wake. Every time a doubly charged baryon was created within the collider, quickly decayed into lighter particles. This new particle was discovered by the LHCb experiment, one of 9 detectors stationed around the LHC's 17-mile-long ring. It's the first new particle seen at the experiment since scientists upgraded the LHCb in 2023. Okay, because well, maybe you shut it down once in a while, and it had kind of been a plague going around for a while, and they shut it down. They upgraded some detectors and stuff because what was it? Like it was Dr. James Beecham before. I remember him. He was on with Professor Keating, and I believe he's a CERN physicist over there. And one of the things he initially said is, I think I'm going to get the magnitude wrong. I think they said they only record 1 out of 40,000 events. It was either 40,000 or 40 million. I realize that's a very large magnitude difference. But long story short, is they can only record so much. They want to record the interesting things and not just the things that they already expect to happen. And you're going to want to do that to get certain precision. You're going to have so many instances of different things happening, and you're going to have to reconstruct it and kind of went over in the little video we posted earlier about what is a measurement. We're attempting to reconstruct two things that hit each other near head on, at close to the speed of light, and then they just shattered into a whole bunch of constituent parts. Oh yeah, and they're like a million billion times smaller than our stuff on our ordinary scale. Good luck. Good luck. It ain't no easy task. All right, let's see. The doubly charmed baryon is only the second baryon with 2 heavy quarks ever seen. The rest have all contained 2 up or down quarks in just one of the heavier flavors. The previous heavy baryon discovered in 2017. All right, so about the past 10 years. Also at LHCb, consisted of 2 charm quarks and an up quark. Oh. Okay. So the difference is if it had 2 charm quarks and an up quark, well, wait a second. 2 charms and up. This is 2 charms and a down. But those are the equivalents of ups. So because no, for the charge to work, uh, because initially I'm just like, okay, that would be the equivalent of a neutron. Despite the similarities, the neutron particle is even less stable than the other heavy baryon with a lifetime predicted to be about 6 times shorter. Okay. Oh, wait a second. Quarks. Families. Okay, so that okay, so this is the confusing part. Because all these things here, basically in order to have a oh, oh. Wait a second. We need to either have two of these, either two of the top ones and one of the bottom ones, because that's what we're talking about here. Because actually, yeah, we got two charms and then a down. It's going to be a heavy proton because two ups and a down would be a proton, right? And two ups and down is a proton. Okay, but if it's saying two charm quarks and an up, hmm, well, that seems strange. Because if we had two charms, like, shouldn't it be one up and two strange? Or it's two-thirds, two-thirds. Two-thirds times three is six. Six divided by three, that would give it a different charge, so hold on. 3x. Two-thirds. It's gonna give us two, right? Yeah. So does it have? Hold on, we need to go to this. Just because this doesn't kind of, oh god, scientific or oh, thank you. And just one of the heavier. The previous heavy bet was also LHCb consists of two charm quarks and up quark. Two charms and up. LHCb, two charm quark, one up quark. 2017. 2017. These are the key words. Hmm. Take out the prefactors. LHCb. Okay, that doesn't make sense because that seems to net out to the more charge, like an elementary charge at two. Maybe that is it. LHC. Okay. 17 result. That was actually from 2016. It's charm. Here we go. This looks like it. All right. LH this from 2017. LHCb is charm to announce observations of a new particle with two heavy quarks. All right. Okay. Oh, so it actually is. I think it actually. Okay, so that I okay that. So the plus was plus one elementary charge, just because I'm literally just reading in the same notation. The GCC plus plus, GCC plus plus is a particle containing two charm quarks and one up quark. That is interesting because at first I thought they were going to say too strange and enough because well, that would be the equivalent of a heavier neutron. But this is a doubly charged proton. It's got two elementary charges there because it's got the plus and plus. Okay, so that math must be correct. Okay. Oh, I did not know that. Wow. And the other one decayed faster? That's weird. Science is amazing. All right. Finish. So it says CERN's Large Hadron Collider reported the observation of the ZCC++. All right. Particles contain two charm quarks and one up quark. The existence of this particle from the baryon family was expected by current theories, but physicists have been looking for such baryons with two heavy quarks for many years. The mass of the newly identified particle is about uh, 3,621 mega electron volts, which is almost 4 times heavier than the most familiar baryon, the proton. A problem that arises from its doubly charged, charmed quark content. Okay, so when I say doubly charged earlier by mistake, I must have been referring to this. Of course, the universe is giving us a hint, or I just think about charge too much, so rather than charm, my mind automatically goes to charge to fill in the blank because I'm just a big lame language model. Okay. It is the first time that such a particle has been unambiguously detected. Nearly all the matter we see around us is made of baryons, which are common particles composed of three quarks. Best known being protons and neutrons, but there are 6 types of existing quarks, and theoretically, many different combinations could form other kinds of baryons. Baryons so far observed are made of, at most, one heavy quark. Okay, so this was the first instance about a decade ago that we saw two heavy quarks. Okay, now we've got the down constituent. Okay, so if we assume, finding the up and down quark differences are, okay. So the down quark has a slightly higher mass. It's a little over twice the up quark's mass. I'm sorry. I'm just curious. Quark mass down quark mass. I mean, I really haven't spent much time on the quark. All right, so like 47%. Convert that. Like a little over 2. All right, so about 2.1. Okay. Cool. And all that binding energy unites them. A mu proton. I see what you did there. A mu proton. I don't think it has a mu on there. Kali, welcome. I was watching your video earlier. I enjoyed it. I'm not gonna lie, you could just talk for an hour. I could just take it like ASMR and stuff, and I'll pick up different little things that I didn't know. So it's always fun. But okay. All right, so we figured that out. Now the question is, why is this lasting longer? Oh no, why is this one lasting less long? Just because it has more mass? Is that generally the thing? Even if the other one had double the charge? See, I didn't know that. I'm like, okay, I guess that makes sense. If you're gonna add it up and add twice the charge, that's yeah. I did not know that. That's very cool. All right. All right. That was the link there. All right. Well, let's continue. All right. I learned something new. I heard about this the other day, and it shows what I know. I'm not a particle physicist. Okay. Despite the similarity, newfound particle is even less stable. Lifetime predicted to be about 6 times shorter. Okay. I mean, the heavier things tend to decay a heck of a lot faster. So, that's why, like, our knowledge of like the top quark's mass or the tau leptons mass, it's a lot less significant digits than the next one up. So yeah, we got a certain precision, but muon we've got pretty good data too. Electron we've got pretty good data too. Up and down quarks, okay, we got some pretty good data. Um, it depends, it's not an easy thing, especially if you're doing a hadron collider. Hadron collider, you got all that other stuff that could turn into. You have just a lepton collider, it's like, well, if a lepton is a base elementary particle, there's only so much. Basically, you knew everything that was going in through all the different collisions. So in order to get precision measurements, if we know the input, whether it's just electrons or muons, we at least know what's going in. So as we get things out, that's the whole. If you hear folks saying that we need a Higgs boson factory, they're basically typically talking about it may be just the upgrade LHC, but often something with like a lepton collider that we can have extremely high precision measurements for to probe like the Higgs and the weak sector. Um, Long story short, is because we don't got to deal with the quarks, and the quarks are a crazy thing, an idea, and well, we hear it's three quarks, but then you'll hear folks say, "No, well, actually, in the proton, there's a sea of quarks." What does that mean? Oh, it's odd, it's flipping, it's going through, it's positive, it's negative, it's an up, it's a down, it's this, it's this, it's this, it's all existing in some seething pattern that allows a proton, or what we consider a proton, whatever it may or may not be, to do its thing. It's kind of complicated, it sounds. I remember, what was it? One day, was it at the monastery? Was it Thad, Echelon, and myself were like, well, let's let's figure out what's going on with like the strong force here. So we've got these gluons, we've got like these quarks and everything. Can we figure out? It was a fantastic mental exercise. We're coming at it from all different perspectives. Long story short, we didn't figure it out. Why? It's freaking complicated. It's a listen. I've heard folks purport different ideas. I know. I think we've. I should have Curtis on at some point. He's a gentleman that how was he? He was originally going for like the PhD in physics and stuff, and then he got caught up in I think like nuclear decontamination and everything. Because I think he was going to work on his PhD, and then like the Fukushima disaster happened, and he's like, I should probably focus on nuclear cleanup. But he's got some things. He's using a he's basically building off of John G. Williamson's photonic model of the electron using a trefoil knot. Um, for some reason, I'm very biased to that, and actually, Kali was the first person who was talking about it. It's like, yeah, why don't light just automatically like why does it seem to have trouble or why is it limited to 90 degrees? It's like, what happened? I'm like, wait a second, 90 degrees. I'm like, that sounds like squaring something. It's almost like if you get the speed of light and you were to literally square it, what might happen? Is that how we get matter? Apparently, from energy, we have actually detected mass. So that appears to be a thing. It doesn't seem to be easy, but it's very interesting because if you get a particle and you get an antiparticle and they come together in just the right way, they annihilate with maximum efficiency, aka not like the one or a couple of percent from like nuclear fission or even a couple more percent maybe from fusion or something. No, 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 no. Those particle and antiparticle annihilate with 100% efficiency. What do we get? Light, photons, whatever that may or may not be. So does that not lead to the just, I don't know, the educative guess of, well, due to complete annihilation, we can get photons out of these things. What if they were made of light? That doesn't seem to be the first out there guess. Now, plenty of folks disagree with that, but John G. Williamson, he's like, well, seems to make some sense. And one of the things he was using was like the Compton wavelength, saying that yes, it is a definitional thing. However, the interesting thing that happens is utilizing the Compton wavelength for things, we do get a very interesting point. You get the point where either was it you either like multiply or divide by like defined structure constant. You're gonna get like the Bohr or the classical radius of the electron, which apparently are things that we do actually like have measured. Um, so it's an interesting thing. And then you take like the proton, um, oh, what is it? The Compton wavelength of the proton, you divide it by like 4 pi, divide by 8. Or basically, you multiply it by pi, divide by 2, like Professor Unziker has said. Uh, you basically get the measured charge radius of the proton, which before we thought it was like, was it like 0.87 femtometers, but it seems more recent experiments, it's seems to be maybe a wee bit smaller, about 0.84 femtometers. That's 10 to the minus 16 meters. That's why I'm saying, like, to reconstruct what's going on when you smash two protons or whatever we associate with being a proton together, it seems to, yeah, it's a million billion times smaller than like stuff on our scale. This mug is like what, like a third of a meter or something like that, zero point 0.3 meters. Yeah, yeah, yeah. Try going down to like a million billion times. It's going to be very hard to drink my coffee. It's won't even get a molecule. That would make me a very sad, sad boy. Okay, where are we? I'm done. I think I'm done ranting for that. Let's see. Let's wrap this up and we can all we can go play with my friend Piper. All right. Finding these kinds of particles helps teach physicists about the strong force, which is the most powerful force in nature. It binds hadrons together. The strong force is also the most mysterious and confusing force, governed by a complex theory called quantum chromodynamics. Just hope to understand how the strong force holds quarks together and how the composite particles' properties, such as mass and spin, arise. This is not the discovery this week at the uh, Moriond Particle Physics Conference in Italy. All right. Very cool. Well, thank you, Clara. All right. There's an tutorial over there. All right. So let's go to the LHCb itself, aka the Large Hadron Collider Beauty Experiment. Why? Well, who doesn't like beautiful things? And again, perhaps it's in the eye of the beholder. A little D&D reference for y'all. Let's embiggen this. I'm such a boomer. I'm literally just realizing now that I could just do it. I've done plus this whole time to him rather than zooming in doing all. Wow, I'm so stupid. All right, so this was from March 17th, so yesterday, by Bolek Pidrichzitska. Apologies for butchering your name. All right, today at the Recontras de Moronoid Electro Week meeting, try saying that 5 times fast, the upgraded LHCb experiment at CERN announced its first particle discovery, a new kind of heavy proton-like particle known as the GCC+. All right. To appreciate what makes this particle special, it helps to recall how an ordinary proton is built. Proton contains 3 quarks, 2 up quarks and 1 down quark, aka up, up, down. For those of us that have played plenty of video games, it's like if you have a Nintendo controller or an Xbox or play up, up, down. That's the code. Up and down quarks are so light that most of the proton's mass come not from the quarks themselves, but from the swirling energy of quarks and gluons inside. Thanks to Einstein's famous equation, E equals mc squared, the internal energy contributes directly to the proton's mass. The newly observed Z, CC plus, is like a proton that has undergone a dramatic quark upgrade. In place of its two up quarks, it carries two heavy charm quarks, giving it a quark composition of CCD. Not the same CCD that a lot of you may have done when you were younger. I digress. Charm quarks are the heavy relatives of up quarks. They have the same charge and properties, but a larger mass and come from the next generation in the standard model. Because charm quarks are far heavier than up quarks. The GCC plus weighs roughly 4 times more than an ordinary proton. We have our beautiful picture here, and then we should have the next picture. Oh, it's the proton family tree. Da, 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 da. I never learned how to snap well. I'm sorry, I can't do the Adams family thing. But basically, okay, so apparently, Rutherford planted this tree in 1917. We had our original protons. Up, up, down. That's our code. Two up quarks, one down quark. Go forward. Then we had, this is the lambda charm plus. There's an up quark, a charm quark, and a down quark. And then we went over here. We got the sigma. How do I pronounce that again? Was it the summation symbol? Summation symbol name. Yeah, sigma. Okay. It's all these things where I'm like, I think I know, but I'm like, when you learn a long time ago, it's like, if I'm going to start saying it, that's the only reason why I know what that G was. Because if you go into the article, okay, you look at this symbol, you're like, what is this? I had to learn this from my Wolfram Summer School project, just because within Wolfram physics, this is basically the scaling term that scales the Planck units to what is conjectured to be the elementary units of stuff. So, like, long story short is I just used the Planck flux for this. Divide the units out and just use it as a count. And then when I plugged into the formulation, it appeared to replicate the original estimates within about 1 order of magnitude. The methodology was completely different and tends to infer a completely different thing. But again, as I stated in that project, it was a highly speculative hack. Now, as long as you caveat what you're doing, you can say some pretty crazy things. But if I'm just going to say, well, this is the way it is. Well, number one, I've inferred a preferred unit basis. And number two, it would infer like this seemed to be more on an elementary level of the minimum of stuff. Even Wolfram and a lot of the original folks in the physics project, it was estimated using like the age of the observable universe. So actually, to be fair, if you take it literally, if the universe is expanding, and that is the scaling term used depending on where you are in the lifetime of the universe, technically that G would scale with that. That would technically mean that, well, wouldn't that mean the constants of nature are changing? But then again, at that point, I'm like, but if they're all changing consistent with one another, doesn't this go back to like the thought experiment where it's like everything is expanding? Is Brooklyn expanding? Yes, at a very high rate. What do we even know? If everything is growing and everything is adjusting by the scaling factor, and I remember I brought that up to Professor Wolfram at the time. It's like this is like, yeah, this is going to require some more thought at one point or another. But it's like for him, to my knowledge, and again, you'd have to ask Stephen Wolfram himself. His big thing is finding the patterns, and what is believed to it, as long as he can at least conceptualize the underlying rules for a particular phenomenon, whether that be in physics, biology, whatever it might be. That is the method he's using and he happens to be a tech CEO with some resources and a fairly famous scientist. So he has the benefit of if he wants to investigate cool things, he loves to do that. And if folks want to help him figure out cool stuff, then he's happy to work with different folks and build upon different things. I just thought it was interesting that from a completely different angle, you're able to basically replicate things, but one is assuming basically a minimum. They were assuming a maximum time component. Why the heck should any of these things line up? And that would be future work, and I probably should actually submit that to the Wolfram Complex Systems Journal, the Complex Systems Journal, um, because he even told us to. And I just need to clean it up more, and I got to work on that. Actually, I'll do that in tandem with the Core One contest, just because I know depending on how things go, I know there's somebody else working on a very video I've been helping out with. A couple other folks kind of gone back and forth, so I'm going to be helping some other folks out. One of those videos I may just publish over here, but it's one submission per YouTube channel. I'm going to go through the units thing and upgrade that to something much more detailed that I could feel comfortable submitting to an actual journal. And if I can submit to an actual journal, that means guess what in turn? I could actually submit it to the Core One content. Oh, maybe I'll just explain the Wolfram physics thing. Maybe I'll just do that. And I do have, actually, if I'm submitting it, and that was from a Wolfram program, it's another way to conceptualize things. Yes, nerdy. Welcome, my friend. It's all hack. It's. I don't want to say that's what Professor Feynman said about like Feynman diagrams, but it's interesting because Stephen Wolfram was kind of. I don't want to say he was his apprentice, but they were friends and they worked together at I think was it Caltech and maybe the Institute for Advanced Study, and then even here on the East Coast for a while for like thinking machines or something. And even Dick Feynman would say it's like Feynman diagrams have to be the stupidest way of calculating these things. I just haven't found a better way yet. We still use it to this day, trying to account for all the different stuff and things that are going on. Taurus universe. I'm very biased to that. I tend to think that might be what's going on, and occasionally the terrifying thing is, and again, this right here, this is just speculation on my part. Okay, hold on. Let me take that down so we can clarify. Let's just speculate. Hold on. I have the primer. Where is this? Okay. Buckle up, everybody. We're going to conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper turtles all the way down.
Yes, it's on the back of an infinite number of hyperruleal turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
All right. So I forgot what I was speculating. Oh, the speculation is every once in a while. Okay. When I didn't really, okay, the more I learn about things, the more I tend to be a little bit more careful, because you can just hear something and you can just rant like nobody's business. And if you say something with conviction and confidence, at least from what I learned with corporate sales, a lot of times people will just believe you. And again, there's a lot of different dynamics. Some folks, maybe they're more preferential, perhaps they're in a spot. Maybe they just, it sounded good and you don't know anything else. The person seems kind of cool. Sure, of course I got to believe. I know this person. I trust this person. A lot of it might be BS, but I go back to thinking some of the crazy things I was saying and I caveated it. And then I kind of loop back around and I'm like, the terrifying thing is what if just a rough analysis, even if I wasn't thinking about it right, what if some of those words were accurate? It's a terrifying thing. But again, I'm biased. I don't have evidence for that. The interesting thing about if I take Thad's model literally, we might actually be cycling through a universe. It might kind of be like the hyperbolic figure 8 nod, and maybe I don't know, who do we live in the 4-dimensional content? Because even if you do the hypersphere, basically, the interesting thing is if you take the radius. Okay, hold on, let's do this. I think I have this bookmarked. I'm sorry, we're in the speculation part of the video. Okay, let's just go to one of the first things I have. All right, bring that up. All right, so this here. This is basically, what is this? This is a 4-dimensional hypersphere, and I took one of Thad's calculated numbers for the Planck length. I took it to like, I don't know, like 60 digits or something like that. And again, it's a conjectured closed form, but at least the first 5 or so digits should work. So basically that's inverted over meters. So basically the claim is if the Planck length is the minimum, we have to claim, and again, I'm going to be outright about this. This suggests, or the claim would be, there is a preferred basis. Like at that point, we are saying the meter is significant. Why? I mean, again, you can just say, well, it's an artifact because the original kilogram was based upon water, because the conventional value of water, quote unquote conventional, is 1 gram of water is 1 cubic centimeter. So literally, just like the old diagrams, how it's like, all right, you got a row of 10, now you get 10 grams. And then you take 10 of those rows, you're going to have 100 grams. Okay, now you take those 100 grams and you build it up 10 levels. Oh, now you're going to have, you're going to have a lot more. You're going to have a kilogram, 1,000 grams. Okay. That's basically 10 deciliters of water. You go to a full meter, it's going to be 1,000 kilograms because that's that 1,000 prefix on it. Okay. But again, that was just our original basis. I think it was Cavendish, because I think Newton originally, he had the mass 1 times mass 2 divided by your R squared and everything. He didn't actually instantiate any units. Cavendish was actually doing the experiment to attempt to measure the gravitational force on Earth. He was like, the torsion balances, which is still insane to me that anybody could do that. But apparently Thad had said, I think in college they were trying to do that, and to get it to like even like 2 significant digits was like ridiculous. But yeah, he was utilizing basically the density of water, basically the mass of water, and assuming it's 1 gram is equal to 1 cubic centimeter. So that is an artifact, but then again, if you do the whole quote-unquote spherical god cow interesting thing, you're taking the mass energy of the Higgs, and then you're assuming you're using its full Compton wavelength divided by 4 pi r cubed, blah, 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 blah. You do that little trick, and then you multiply it by the Einstein kappa constant, so basically 8 pi divided by the Planck force, and you coincidentally get out approximately 1 over meters squared. It's really damn close. So you take the square root of that, you're probably gonna get a little closer to a meter. See, that's where I would say maybe the meter is significant, because there's also a lot of coinkydinks. If you just use our base units, we got some really good. There's some interesting coinkydinks there, where maybe that explains something. But again, I realize I just went on a 3-minute caveat there. Let's wrap this up. So what's the claim? If you take a 4-dimensional hypersphere in 4-dimensional space, long story short is you get content in 4 dimensions. Okay. Now, let's get a hypersurface area. Okay. But if you notice, you get this diameter here. Hold on, let me take off a lot of these digits. We don't need all that there. Like that. There we go. All right. I need to put it in 4 dimensions. And caveats are important. Where are we? Where it is very interesting. Oh, we got a Pilgrim Dan. What's going on, Dan? And our rodent. It is fine. Yes, wait, watch out for those phase dimensions. Listen, just because I've claimed to have been deliberately breaking the multiverse doesn't mean that it's true. Yeah, but that's the thing, Dan. The sheer fact that we can even attempt to figure this out and seem to make any progress is freaking insane. Like, I just even remember when I was a kid, it's like, yeah, you want to get those channels. You want to make sure you got that fancy dandy antenna on your roof, because otherwise you're just going to get some fuzz. Why? Cosmic microwave background or something it is a fascinating thing. And yes, maybe it is waves all the way down. Pun intended. Okay, so the whole point is, okay, so for a four-dimensional hypersphere, assuming this, we get this out. They get a diameter about 10 to the 35 meters. Why am I showing you any of this? All right. So if we coincidentally do this, so let's take Planck mass. We're going to scale it by meters over the Planck length. And again, this is probably why it's happening. We're squaring it. Long story short is you get like 8 times 10 to the 61 kilograms. Okay. When you do it more significant digits, you're going to see something like this. 8.3315 times 10 to the 61 kilograms. Okay. So kilogram black hole. And again, I scaled it literally by meter squared over Planck length. So full disclosure. The kind of fun thing is, you look at the horizon radius. Wait a second. 1.237 times 10 to the 35 meters. 1.237 times 10 to the 35 meters. So, listen, I can be critical of, it's like, do we live inside a black hole? I don't know. But very often if I'm going to take a large number, let me look at it through the lens of, if we did live within a black hole, what may we expect? Now, I don't know that, but it's just fun that I instantiate that radius for this, and it basically just multiplies it by 2 to give you the diameter. And then when you put in the mass there, and again, this would be assuming like the Planck force is a constant. So maybe there's an 8 pi factor in there, but it gives you the same thing. But I'm also pretty sure that this is probably literally just because of what I put into it. What I put into it? Well, I'm squaring meters here, because if you do that, we get that number. Yeah, 3.8 times 10 to the 69. That's all I did here. Because this whole dang thing is 3.8 times 10 to the 69, because I did the same thing. But it's interesting where you're putting in the same components. It does seem to fit. So it's interesting that these things kind of line up there. It's like, well, again, the black hole is that factor of 2 there, because if you just do normal black hole, the formula for the event horizon, it's got the 2gm divided by c squared. So yeah, 2 gravitational constant, your mass, c squared. So for every unit of mass, the radius of the event horizon doubles. So for every Planck mass, you get 2 Planck lengths. So that's why a minimal black hole is going to be like one of the densest things. You try to cram the Planck density, and it just automatically seems to just like pop out and be like twice the radius of the Planck volume. Is that error correction? Is that error prevention? I don't know. But it's interesting that it does increase that way. So, okay, to bring it all the way around, it's maybe we do have a cycle that maybe the grand unified folks were right. And when I say that is maybe proton decay does happen after 10 to the 35 years. Looking at it, if that's the cycle and there is a knot or something that within physics some may view as a quote-unquote Einstein-Rosen bridge. I just think it's where, according to Thad's calculation, there's a point where it gets down to about the charge radius of a neutron. Now, I'm just thinking that if you have a later thing where there's a whole bunch of supermassive, ultramassive black holes, if they were to get to this point where basically it's like stuff goes in, gets extraordinarily crunched down, and may come out as, I don't know, maybe a hot, dense state of quark gluon plasma or something like that. And I tend to think where that might be where the observed cosmological constant is. Because if we are at a maximal state, you get stuff coming in, it's getting crunched down, hot stuff comes out, cool stuff loops back around. The interesting thing also is in the Wolfram Physics Project, a maximally entangled observer. It's that picture I used with Steven in a double-covered hypergraph. It's basically the elementary frequency, but they think of it, they quote it in thinking about as times actually action. So long story short, is a maximally entangled observer would be thought to be some sort of astronomical event putting out the Planck power. The Planck power is a Planck energy per Planck second or Planck time. Okay. For instance, the Planck power is like 10 to the 52 watts. How much is that? All right. Planck power. This is energy per second. So in 1 second, it's putting out that much. So let's just multiply by seconds. We multiply by 1 second. Okay. So we're putting out that much energy per second. What is that? That's 1 Planck energy per Planck time. So there's a lot of Planck times in this, aka, watch this, divide by Planck time, we should get Planck energy. Oh, no, we need I did it wrong. We need to multiply by the Planck time. There we go. Okay. Oh, still did it wrong. Wrong dimensions. Long story short is, hold on. It's because I had seconds in there. There we go. Now it'll be Planck energy. Oh. Unit. There we go. Planck energy. Bada boom. All right. But since there's about 5 times 10 to the 44 Planck seconds, if you would, within 1 second, that's why you have this ginormous number here. Okay. That joules. How much mass is that? Hold on. Mass energy. All right. That's like 10 to the 35 kilograms. So the interesting thing is if we take that, we take mass of Sagittarius A star. Let's divide it. I think that's spelled wrong. Let's Sagittarius. There we go. Okay. So basically, if we took Sagittarius A star, was thought to be the supermassive black hole at the center of our galaxy. It's like 4 million solar masses. So hypothetically, a maximally entangled observer, if it's outputting the Planck power, it would output in mass energy the total mass of Sagittarius A star in 21 seconds. Dang. So my general thought is a universe kind of recycles itself. And then if you're outputting that as a limit there, you could explain a lot of other phenomena if you just assume the cycle. Again, there's a lot of ifs in there and speculation, but that's the universal hot pocket toast. Oh, that's silly. Where were we at? Okay, so that was the plus one. All right. Okay. Okay. So this was that was a home article. Where was the other guy? Okay, the proton family tree. The image above left shows the arc of this exotic particle. Protons, quarks with strange charm, and bottom in this picture, the G CC plus it's near the very top where both of the protons light up, and the quarks have been swapped out for charm. Okay, so basically we got this data, we get a blip in the data. That's basically how we're trying to reconstruct this. So it's not an easy thing. So we can see there it's okay. So yeah, basically it's in the range of the other mass of that other what is it? The G CC one. That marks the first new particle identified with the upgrade LHCb detector. Decay into 3 lighter particles. All right. So up, down. All right. The lambda charm plus the K pi meson. So, oh my God, I can actually start to read some of this stuff now. Showing the Feynman diagram above. By reconstructing the combined invariant mass of these decay products shown above, the researchers observed a clear peak of about 915 events around 3,620 MeV divided by c squared. A signal exceeding 7 sigma, well above the threshold required to claim a discovery. Detail fit measured the mass to be. Oh, that's very cool. You get some stuff. As a spin partner. All right. That's 2017, almost identically. Plus, should have nearly the same mass until now. However, observing, 20 years ago. Wow. Okay, so this is the partner of the other guy. All right, we got a full presentation over here. Very cool. I'm not going to lie. I actually didn't even notice this until now. Oh, there's a lot of stuff here. Should probably even just spend time just throwing this in the chat and just breaking it up and going through and using a notebook and maybe doing some calculations, but all right. Yeah, it's the thing. It's like a lot of it's just kind of language, and that's why, like, when the pandemic hit, I just started listening to like lectures from like Professor Sean Carroll, Stephen Wolf. No idea what they're talking about. Just listen to the language, immersing myself in it, and trying to eventually start to learn. And pardon. It also doesn't hurt actually doing some of these calculations, because I can say the words, but then it's like, okay, if I can actually like do a calculation for its radius, or I see something in here, let me do this. Let me look at this. As long as there are some numbers and I can identify the different things, that's probably one of the greatest parts about like an AI agent is like it can tune things to ways you understand. Because I can see a whole bunch of notation. I might not recognize it. Well, what is this? Oh, there's just differentiating between like the speed and this mass or this velocity. There's a given direction here. This is representing these constants of nature in this way. Okay, now we're just taking joules, dividing it by like, I don't know, like meters or something, taking the square root to use force as our scalar and our Lagrangian or something like that. So it's like going through and actually like doing the calculations. It's almost like doing homework and or practice problems may help one learn something. Whoever would imagine that, but okay. So the links to all the stuff is in the doobly-doo below again. Feel free to check it out. I realize we used the last few minutes just for rampant speculation and stuff. Yes. It was under 9,000 mega electron volts. So maybe, yes, it was under 9,000 MeV. I needed to double check my stuff and things there. But all right, everybody, that's all we got for right now. I think I've got it. So we roll over into Piper's got a stream going on. She's bringing back the quote unquote effort show. So somebody would like to join us over there, by all means. If not, take care of yourselves, everybody. It's a wacky and wild world out there, but peace out. It's open for a better tomorrow, everybody. Catch you later.